What if I told you that 90% of the web interface you're building right now is just, well, it's just text?
Sounds completely absurd.
Yeah, exactly. But if your UI looks prickin', you don't need to, hunt down some fancy new React component library.
Right, or add complex CSS animation.
Yeah, you probably just need to fix your typography. So welcome to this deep dive. We've custom tailored this specifically for you, the senior backend engineer who really wants their web apps to look as flawless on the surface as they function under the hood.
Yeah, and today we are diving into Chapter 4 of Web Design for Backend Engineers. And the focus here is entirely on typography.
Which is huge.
It is.
Yeah.
And, you already have a serious toolkit from the earlier chapters we've looked at. You know how to implement visual hierarchy. You understand the mathematical application of white space from Chapter 1.
Right, and you've got alignment, proximity, contrast locked down from Chapter 2.
Exactly. Plus, you know how to run a 15-minute design audit for consistency from Chapter 3. So we're taking all of those structural concepts as a given today.
Because even if your layout is, even if it's mathematically perfect in terms of white space and proximity, if you get this next layer wrong,
the whole thing falls apart.
the entire application just feels broken. And the source material drops that massive claim right out of the gate. Like we mentioned, typography is 90% of web design.
Which, as an engineer who spends days optimizing database queries and wiring up complex state management,
Does that percentage feel completely hyperbolic?
it really does. But take a step back and run a mental inventory of, say, a typical SaaS dashboard or an internal admin tool.
Okay.
Look at what the user's actually consuming. The navigation menu on the sidebar.
That's text.
Right, the primary heading summarizing the data. Text. When a user interacts with a complex form to configure a new environment.
The labels are text, the input fields take text, the validation area.
And the final submit button contains text.
Yeah, it's all text. The text is doing all the heavy lifting here. It's the primary vehicle for data transfer between the system and the human.
Exactly. The source makes this really compelling argument that if your typography is structured perfectly, your page looks polished, even if every single other element is stripped down to bare HTML.
Because typography is the raw material of your interface. And, okay, let's unpack this with a brilliant analogy from the source.
Oh, the production logs analogy. I love this one.
It's so good. Think of typography as the logging in your production system. If your log formats are clean, strictly typed, deeply consistent, logically structured.
You can diagnose issues without a fancy dashboard.
Right. You don't need a massive Grafana setup if the logs are perfectly readable. But if your log data is unstructured string data, inconsistent keys, random formatting...
A complete mess.
Yeah, then no dashboard can save you. The entire system has to work overtime to parse it.
And if we connect this to the bigger picture, typography functions exactly like that log format for the user's visual processing. If it's inconsistent, if the visual hierarchy doesn't follow a strict logic,
the user's brain has to constantly parse and reevaluate what they're looking at.
They're literally burning cognitive CPU cycles just trying to figure out what is a heading and what is a button.
Exactly. But when you define a strict typographic schema, everything you build on top of it, the data tables, the modal windows, all the complex charts, it just falls naturally into place.
It works effortlessly. But if you get it wrong, you're fighting an uphill battle against your own UI, and no amount of expensive custom graphics can patch a broken schema.
So to build that schema, we have to start with the atomic unit, right? The visual syntax of the text itself.
Yes. Figuring out what the text should actually look like. We need to categorize fonts into their fundamental architectural families.
Okay, so we're talking about serif versus sans-serif. Choosing your syntax.
Exactly. And to understand the functional difference, you just have to look at the geometry of the letter forms. The first family, serif fonts, features these small decorative strokes.
The little feet on the edges of the letters.
Right, the feet. Extensions at the ends of the main vertical and horizontal lines.
Like Times New Roman, Georgia, Garamond.
Those are the classic examples, yeah. And historically, these typefaces were designed for the physical printing press. They carry this really heavy psychological association with tradition, authority, editorial gravitas.
Which is why the New York Times uses complex serif fonts for their digital headlines.
Exactly, to leverage that legacy of print journalism. And platforms like Medium use serif fonts for long-form article body text to, mimic the immersive experience of reading a physical book.
Right, but then the second family is sans-serif, and sans is French for without, so these are letter forms completely stripped of those decorative feet.
Arial, Helvetica, Roboto.
Yeah, defined by clean, uniform, straight lines. And here's where it gets really interesting. For web applications in 2026, the source dictates a very clear standard. Sans-serif is the undisputed default.
And that standard exists for a deeply technical reason. It involves how screens render graphics.
Because displays are fundamentally grids of square pixels.
Right, so when you try to render the delicate tapering curves of a serif on a standard 1080p monitor, especially at a small size like 14 or 16 pixels, the screen just doesn't have enough physical pixels to draw those tiny curves smoothly.
You end up with anti-aliasing artifacts. The browser tries to blur the edges of the pixels to fake the curve, and the text ends up looking, well, muddy or blurry.
Yeah, it's rough. But sans-serif fonts bypass that rendering limitation. Because their lines are largely straight and uniform in thickness, they snap much more cleanly to the pixel grid of a monitor.
So the text remains brutally sharp.
Highly legible, even on lower resolution displays or dense mobile screens.
Plus, it strips away that historical editorial baggage, right?
Right.
Leaving a modern aesthetic that aligns with the functional nature of a software interface.
Exactly.
But let me push back on this for a second. Because as engineers, we love strict rules, but we also deal with edge cases constantly.
Sure.
If I'm building a dashboard or a B2B SaaS tool, is there ever a real practical reason to use a serif font? Or should I treat use sans-serif as a strict, unbendable linter rule?
I mean, for the vast majority of software products, you should treat it as a hard rule. You are optimizing for clarity and rapid data consumption.
Okay.
Serifs introduce visual noise that slows down scanning. The only exception in a software context is if you're building an application that explicitly trades in tradition or extreme luxury.
Like a boutique wealth management portal.
Right, or an application generating complex legal contracts where the document must feel highly authoritative. Otherwise, stick to sans-serif.
Fair enough. And the source material highlights one specific open-source sans-serif font called Inter. They call it the modern industry standard.
Yeah, Inter is incredible. It was purpose-built from the ground up for computer screens. The designer, Rasmus Andersson, obsessively engineered the X height.
Wait, X height?
Oh, that's the height of the lowercase letters compared to the uppercase letters.
Ah, got it.
He optimized it to maximize legibility at tiny sizes. So if you're an engineer who doesn't want to spend 3 hours browsing font foundries, you don't need to overthink this. Inter is your safe, highly optimized default.
Okay, I'm sold on Inter. I want to use it as my visual syntax, but my immediate back-end reflex kicks in here regarding, well, latency and deployment.
How do we actually serve this font to the user?
Exactly. How much is downloading this asset going to block my page render?
You're identifying the core friction point of web typography right there, the delivery mechanism. You essentially have two fundamentally different architectural approaches to serving fonts.
And it maps perfectly to back-end dependency management. You're choosing between relying on a system's native standard library versus fetching a third-party package over the network.
That's a great way to put it. The first approach is the standard library, the system font stack.
Where you instruct the user's browser to typically utilize whatever native default font is already deeply integrated into their operating system.
Right, so if my user's on a Mac, their browser instantly pulls up San Francisco.
If they're on Windows, it renders Sego UI Android phone, it grabs Roboto.
Exactly.
But here's my issue with that. As a back-end developer, I despise non-deterministic outputs. I write a function, I expect the exact same output every time.
Naturally.
If I use a system font stack, my UI looks physically different depending on the user's hardware. Why would I ever intentionally design a system where the visual output is non-deterministic?
Well, what's fascinating here is that you accept the visual variance because the performance gain is absolute. When you utilize a system font stack, the network cost is literal zero.
Zero.
No DNS resolution, no TCP connection to a font server, 0 bytes downloaded. The text renders the exact millisecond the HTML is parsed.
The latency is practically negative because the asset is already in the OS memory.
Furthermore, Apple, Microsoft, and Google have invested tens of millions of dollars into engineering these specific typefaces.
Right, they're highly legible.
Perfectly hinted for their respective operating systems. And crucially, your user is already implicitly familiar with them. It's the exact font they spend 8 hours a day reading on their native OS menus.
So the cognitive friction of reading your app drops to zero.
Exactly. GitHub uses a system font stack. High-performance internal tools almost universally use them. You are trading pixel-perfect cross-platform consistency for raw, unadulterated speed.
Okay, wow. But the alternative is the NPM package approach, right? Utilizing a web font delivery service, typically Google Fonts.
Right.
If I absolutely require my dashboard to look completely identical on a MacBook, a Dell laptop, and a Linux server, I have to provide the font asset over the wire.
That is where you reach for Google Fonts. You mentioned Inter earlier, it's available there. Other highly readable functional sans-serif options for body text include Roboto, Open Sans, or Lotto.
And for headings, where the text is physically larger and you might want to inject a tiny bit of brand identity, the source suggests geometric sans serifs like Poppins, Manrope, or DM Sans.
Great choices.
But let's look closely at the cost of this identity. It's not just a matter of adding a few hundred kilobytes to the payload size, is it?
No, it's about how the browser handles that network request. The performance penalty of web fonts is significant if not managed correctly.
Right.
When a browser encounters a Google font link in your HTML, it has to resolve the domain, establish an SSL connection, download a CSS file, parse that CSS to find the actual font file URL, and then download the binary itself.
And while all that network traffic is happening, the browser has a massive rendering dilemma.
It has to decide what to show the user. Historically, browsers would just hide the text entirely until the custom font finished downloading.
Creating FOIT, the flash of invisible text.
Exactly. Your user is staring at a blank, broken screen, waiting for a typography asset to load just so they can read a basic paragraph.
Which is terrible. But the modern alternative isn't much better, is it?
Not really. The browser shows a native system font as a fallback, and then when the Google font finally arrives over the network, it violently swaps them out.
Which creates FOUT, the flash of unstyled text.
Yes, because the custom font and the system font have different microscopic dimensions. Swapping them forces the browser to recalculate the entire page layout.
Buttons shift, paragraphs change length, the UI jumps around. It feels incredibly janky to the user.
So the trade-off is stark. A system font stack gives you instant, zero-shift rendering at the cost of cross-platform consistency. Google fonts give you total visual control at the cost of network latency and potential layout shifts.
And this leads directly to the ultimate developer pitfall when they discover Google Fonts, the candy store effect.
Oh, it's so common. You scroll through the repository, you see this incredibly stylized, complex display font, and you think, wow, that looks incredibly modern.
And then you pull it into your sauce application and apply it globally to your 16-pixel body text.
And you instantly destroy your application's usability. Fonts that look phenomenal at 100 pixels on a marketing poster often become illegible smudges at 16 pixels on a dense data table.
Yeah, you incur all the network penalties of FOIT and FOUT just to serve text the user can barely even read.
Exactly. As a baseline rule, limit your application to a maximum of 2 font families, usually just one highly legible sans serif for everything, and never, ever use decorative fonts for 16-pixel functional UI elements.
Okay, so we have our visual syntax locked down. We understand the deployment trade-offs. The final piece of the puzzle here is sizing. How do we determine exactly how big each piece of text should be?
This is the area where developer implementations traditionally devolve into complete chaos.
Oh, tell me about it. If I look at a legacy CSS file from a project that didn't have a design system, the font sizes look like someone just threw darts at a board.
It's terrifying.
There's an H1 tag set to 24 pixels, a subheading at 19 pixels, body text split between 14, 15, and 16 pixels depending on the component, a random span tag floating at 13 pixels.
It's the visual equivalent of scattering hard-coded magic numbers throughout your application logic.
Yes. You would never write a backend service where you just hard code random timeout integers like 432, 512, and 600 directly into the business logic.
Right, you extract those into cleanly defined constant variables based on a specific logic.
But front-end code bases are littered with these arbitrary pixel values. The developer just tweaks the number in the browser inspector up a pixel, down a pixel until it looks okay on their specific monitor, and then they hard code it.
And the resulting UI feels fractured. The user might not be able to articulate exactly why, but they subconsciously recognize that the spacing and sizing lack an underlying logic.
It just feels off.
Designers do not guess these sizes. They solve the magic number problem by implementing a strict mathematical scale, essentially defining UI constants.
And the source introduces this concept as a type scale, specifically a modular scale.
Which is where your engineering brain is going to truly love design. A modular scale functions exactly like a musical scale.
Okay, how so?
In a piano octave, the frequencies of the notes aren't random, right? They follow a specific mathematical progression that makes them inherently harmonious when played in sequence. A type scale applies that exact same harmonic math to visual proportions.
Let's walk through the specific math on this because it is an incredibly elegant engineering solution.
Sure.
You start by defining a single root variable, your base size. And for web application body text, the industry standard is universally 16 pixels.
Right, 16 pixels is your foundation. Every other size in your application will be derived from that root value. Next, you select a mathematical ratio.
Like a multiplier.
Exactly. A highly effective and common ratio in UI design is 1.25, which typography refers to as a major third.
So to generate your scale, you simply multiply your 16 pixel base by 1.25. That outputs 20 pixels. That becomes your variable for small headings or like prominent UI elements like a card title.
And to determine the next size up in the hierarchy, you take that 20 pixels and multiply it by the 1.25 ratio again.
Which gives you 25 pixels. Perfect for a modal header or a secondary page title.
Multiply 25 by 1.25, and you get 31 pixels for your primary H1 page headers. Multiply once more, and you hit 39 pixels for massive empty state display text.
And the math operates in reverse as well, right?
Absolutely. To establish your sizes for secondary text like a subtle timestamp on a log entry or the helper text under a form input, you take your 16 pixel base and divide by 1.25.
Yielding roughly 13 pixels.
Exactly. The chaos is entirely eliminated.
Because instead of infinite random integers scattered everywhere, your entire application is constrained to a predefined, strict set of variables. 13, 16, 20, 25, 31, and 39.
Every single piece of text must map to one of those constants. This is where you leverage CSS custom properties. You define these mathematical outputs as variables in your root CSS file. Or, if you're using a utility framework like Tailwind, these scales are already mathematically pre-configured in the default theme.
So you never write a raw pixel value again.
Never.
And the big takeaway here is that the specific ratio, whether you use 1.25 or 1.333, is less critical than the strict adherence to the system itself.
Because the sizes are mathematically tethered to one another, the interface intrinsically feels cohesive, connected.
It's a beautifully constructed system. So what does this all mean? Let's synthesize the architecture we've built today. We fundamentally reframe typography from a subjective art form into the structured logging of your UI.
We established that sans-serif fonts are the mandatory default for web applications.
Right. Highlighting inter as the optimal, highly engineered standard. And then we analyze the deployment mechanisms.
Weighing the zero latency, instantly rendered performance of a system font stack against the cross-platform determinism and, well, network costs of Google fonts.
And finally, we eradicated magic numbers from our CSS by implementing a modular type scale, using a baseline ratio to size everything.
It translates front-end visual design entirely into back-end system logic.
Right.
But yet this is just the foundational layer.
Wait, there's more.
Oh, definitely. We've defined the structural syntax and the constants, but we haven't touched the micromechanics of reading itself. That's what's coming up for you in chapters 5 and 6.
Oh, right. Once your structural scale is in place, you have to optimize line height, manage font weights, font pairing.
And avoid the subtle typography mistakes that ruin readability. And eventually this scales up into color theory, layout systems, UI components, accessibility, responsive design.
It's a lot. But none of those higher-order abstractions function if the underlying typographic schema is malformed.
Exactly. That underlying structure defines the entire user experience. Which leaves us with a really provocative thought for you to mull over during your next coding session.
Lay it on them.
This raises an important question. If typography is truly 90% of web design, what would happen if you stripped away every single border, background color, and icon from your current project?
Just disabled the CSS for all of it.
Right. Would your application still be perfectly usable through the text alone?